Go ahead and get started. First things first, you can pass your homeworks up front. Yeah. Okay. And Jordan and Logan, just so you know, I got your homework submission okay, so we're good there. Oh, let me get rid of this transcript. And then I do have solutions to pass out. Now, for those of you listening online, I will, well, just for everybody, but particularly for those of you listening online, I will be posting the solutions on Brightspace tonight.
Thank you so much.
Mhm. And try to get these graded by next class. If by chance I don't, it will definitely be by the following class. And also, particularly missing last week, you guys are lucky, no new homework tonight because I didn't think we quite covered enough material to be worthy of a homework. So next week you will get homework number 2. And I think that's it as far as I think that's whoops it as far as administrative stuff. So any questions on that? Okay. So otherwise, and you know, here's my mouse. Here we go. And as far as I know, I shouldn't have, oops, come on, shouldn't have any more travel for a while. So as far as I know, for the next period of time, we'll be just, just chugging along as usual. And also, just so you guys, just to alleviate any worries you may have that, if you follow the news, you've probably heard some talk that there's the potential of a government shutdown, but next week. But my teaching here has nothing to do with my job as with the government. So even if the government shuts down, it will not affect class here in any way. If anything, I'll have a bit more time to devote to class prep and that type of thing. So anyway, so 2 weeks ago, when at our last class we started talking about fracture mechanics, and we first did the very simple English maximum stress type of approach. But as we also talked about, there were some significant deficiencies with that methodology, which is leading to other people to develop alternative methods of doing fracture analysis. So first one we'll talk about is an energy balance approach that was developed by Griffith. And we introduced it, like many other things, we introduced this a little bit in the first lecture when we did the broad overview of the field of fracture mechanics. But anyway, in the Griffith method, he follows the idea that according to the first law of thermodynamics, when a system goes from a non-equilibrium state to an equilibrium state, there'll be a net decrease in energy. And in 1920, Griffith applied this idea to the formation of a crack. So basically what this means is a crack can form or an existing crack can grow only if this process causes the total energy to decrease or to remain constant. Can't create energy. So the critical conditions for fracture are defined as the point where the crack growth occurs under equilibrium conditions with no net change in total energy. So we'll start off, so we'll consider, an infinite plate, infinitely long, infinitely wide with a finite thickness B, and we'll assume that this plate is subjected to a constant stress, sigma, and we'll assume that this plate has a crack of length 2a, as shown in this figure here. And we'll assume that the width of the plate is much greater than 2a, and we're also going to assume that plane stress conditions prevail, so that there's no stresses out of the plane of the paper. So in order for this crack to increase in size, sufficient potential energy has to be available in the plate to overcome the surface energy of the material. So as we talked about two weeks ago in the last class, that there's this inherent atomic energy which holds atomic bonding energy which holds a material together. So you need to apply enough energy to the plate to overcome these atomic bonds in order for a crack to grow. So Griffith defined an energy balance for an incremental increase in the crack area, dA, under equilibrium conditions. And when we talk about the increase in the crack area, we talk that this length 2a and the thickness b, because we were assuming in all this that the crack goes all the way through the thickness of the plate. So the ways to look at it is we can say that the change in the total energy as a function of area is equal to the change in the change in potential energy with respect to area plus the change in the energy due to the work required to create new surfaces with respect to area, and this total change in energy has to be equal to 0. So take one of these terms, move it to the other. So what we say is the negative of the change of potential energy with respect to area is equal to the change in the surface area with respect to area. So as we just said in this equation, E is the total energy, the pi is the potential energy supplied by the internal strain energy and external forces, and that W sub S is the work required to create new surfaces. So for our cracked plate that we talked about above here, Griffith used the stress analysis of Inglis to derive this equation, and we're not going to go through the derivation process, so we'll just say so that the potential energy is equal to the potential energy of the uncracked plate minus pi times the square of the applied stress times the square of half of the crack length multiplied by the thickness of the plate divided by the modulus of the material. And what we can also say is that since the formation of a crack requires the formation of the crack requires the creation of two surfaces, we define the work required to create new surfaces by the below equation. So we say the work required to create surfaces is equal to 4 times the half crack length times the thickness of the plate times our surface energy of the material. And the reason it's 4 here is because what this really is equal to the surface energy times the area, which is 2A, the full crack length times the thickness. And then we have to multiply this by 2 because for, obviously when we look here for a crack, we have 2 surfaces. We have the surface on the bottom, we have the surface on the top of the crack. So what we're going to do is we're going to take these energy equations and we're going to assume a unit thickness. So our original potential energy equation was equal to capital pi times the potential energy of the uncracked plate minus pi times sigma squared times a squared times b divided by E. And what we're going to assume for right now, we're just going to assume that B is equal to 1. So we can say that the negative, just to get rid of this minus sign here, of the derivative of the potential energy with respect to the half crack length A is equal to 2 times pi times sigma squared times A divided by E. And this is just simply, the derivative of A squared is 2A. Everything else is constant. And likewise, we can say that our surface energy is equal to 4 times A times B, which we're assuming is equal to 1, times the surface energy. So if we assume this is equal to 1, then the derivative, So the derivative of our surface energy with respect to the half crack length is just equal to 4 times the surface energy of the material. So now we'll go back. So when we did our quick energy balance discussion, we said that this term has to equal this term. And if it's true for the derivative with respect to the area, it's also true with the respect to the derivative of the half crack length. Let me fix this. Yeah. So B is equal to 1. So what we can do is we can take this term here and set it equal to this term here. And so we have that 2 times, 2 times pi times sigma squared A over E is equal to 4 times the surface energy, and we'll solve for this fracture stress. So we get that sigma squared is equal to 4 E gamma S divided by 2 pi A. The 4 and the 2 cancel out, so it's just 2 E times the surface energy divided by pi times half of the crack length. And we take the square root of both sides. We get that sigma is equal to 2 times E times the surface energy divided by pi times the half crack length, and to the 1/2 power, representing the square root. So this is the failure stress. So for a material, if we know the surface energy, we know the modulus, we know the crack length, pi's pi, we can solve for the stress, for the applied stress that would be required to grow the crack and ultimately fracture the material. Now, in these equations, it's important to note the distinction between crack area, the crack area and the surface area. So the crack area is defined by the projected surface area of the crack, which is twice the crack length times the thickness. But as we hinted at before, a crack has two surfaces. It has a top and a bottom surface. So the surface area of the crack is twice the area of the crack. Okay. So, and okay, and this now that what we went through here was just didn't emphasize it very much, but what we went through here, this was for the case of an, it's blown up a little bit, but it's for the idea of an infinitely sharp crack. Obviously, not all cracks are not all cracks are infinitely sharp, so we have to account for other types and sizes and shapes of cracks. And this is something next week when we start talking about stress intensity factor, based on the geometry of the crack, there's all kinds of different equations for all different kinds of shapes of cracks. But for right now, for this discussion, we're going to talk about one other case. So we talked about in this previous discussion an infinitely sharp crack, but another very common shape of crack is what's called a penny-shaped flaw, where basically it's not a sharp crack, it's more like a circle or an ellipse representative of a penny. And just for a note, we're not going to go through the derivation, but you can also get a similar type of expression for this case, where the failure stress for the case of a penny-shaped crack, and it's pretty similar. It's chi times the modulus times the surface energy divided by 2. Now the difference is we have this extra term in here. This extra term related to the Poisson ratio. So you see, this is pretty similar to what we just developed. The difference is we've shifted where the 2's located. In this original equation, the 2 was in the numerator for the sharp crack. Now for the penny-shaped crack, the 2's in the denominator, and we also have this extra Poisson ratio term running around in there. But one of the important things here is, and you'll see this in a lot of things in our discussion, when we talk about, because the fracture mechanics type of calculations have to deal with the initiation and growth of cracks, one of the things that's very important is in a lot of the things we're going to do, the shape of the crack is going to lead to different results, because just by the nature of the geometry of the crack, different shaped cracks will react to applied stresses differently. So when you see problems or when you do calculations in the real world, it'll be very important to specify the shape of your crack. And obviously it'll be things where when you see in our discussions and when you see tables, things will be idealizations or approximations. Obviously, when you go through, they make these approximations because in a lot of cases, things are pretty close to, sharp cracks occur a lot. What can be called a penny-shaped crack occurs a lot. But obviously, the real world is a lot different than the idealization. So in many cases, you have to pick the type of shape of a crack which is the closest match to something for what you have in your tables, and then go from there. So that's our introduction to the Griffith energy balance. Now we're going to talk about how this criteria is similar and different from what we talked about 2 weeks ago, which was based on a more maximum stress type of criterion. You'll also remember we talked about, and we'll go into more details on this in just a little bit, that the things like the atomic radius was very important in the Inglis type of criteria. So the Griffith criteria is still kind of related to the idea because the Griffith model is based on a global energy balance, and for fracture to occur, the energy stored in the structure must be sufficient to overcome the surface energy of the material. But the truth is still, whether we do it by a stress approach or an energy approach, as I mentioned earlier, fracture still involves breaking atomic bonds. And on the atomic level, where everything happens, the stress on the atomic level must reach or exceed the cohesive stress between your atoms. And we talked about how exceeding the cohesive stress at the crack tip is necessary but not sufficient to cause fracture. So the failure stress equations developed for each of these two methods have a similar form, and the predictions of the global fracture stress from these two approaches are of the same order of magnitude when we're talking about a sharp crack. So for the case of a sharp crack, the Griffith model doesn't explicitly consider the crack tip radius, but the two equations are broadly consistent for each other. So for the Inglis criteria, which was our maximum stress, we said that the failure stress was equal to the modulus times the surface energy times 4 times the half crack length to the 1/2 power, so the square root. And as we just derived so this is with the Inglis, and as we just talked about for the Griffith, we have that the fracture energy for an infinitely sharp crack is 2 times the modulus times the surface energy divided by pi times the half crack length. So the equations are different in some of the and almost forgot the square root. So these equations are different in obviously there are differences between these equations, but still the square root, they're still both to the square root type of power. They both have modulus and surface energy, and they're both related to the crack length. And again, and a reminder, this is for a sharp crack. Now, here's where, and we're going to be doing a couple things with this picture, but for right now, the thing to note is that a contradiction emerges when the crack tip radius is significantly greater than the atomic spacing. So for example, this is obviously blown up a lot for exaggeration, but you can see here that our radius of curvature here is not infinite. There is a radius of curvature, and this radius is significantly greater than the atomic spacing. And so the change in stored energy with the crack tip formation is insensitive to the notched radius as long as the length of the crack is significantly greater than the thickness. And the Griffith model implies, because we don't have anything in there in either the sharp crack or a penny-shaped crack, we have nothing in there talking about the atomic radius, so that the Griffith model implies that the fracture stress is insensitive to the radius of curvature. So, but according to the Inglis analysis, for the cohesive stress to be obtained at the tip of this notch, the Inglis criteria specified that the global stress leading at the notch tip is equal to twice the applied stress multiplied by the ratio of the square root of half the crack length to the radius of curvature. So we talked about last time that with the Inglis criteria, this stress right here at the tip of the crack, sigma sub A, is significantly influenced by the radius of curvature. But in the equation, as I said, the equations we talked about with the Griffith criteria, nothing here is there's nothing representative of the radius of curvature. So just for an example, consider a crack with this rho, this crack radius here, given to 5 times 10 to the negative 6, so 0.005 millimeters if I'm doing my calculations correctly. So a crack like this, if you looked at it under a microscope, would appear to be very sharp. I mean, 5 times 10 to the negative 6 is a pretty small radius of curvature. It's 1,000th of a millimeter. However, this radius of curvature is still 4 orders of magnitude larger than the atomic spacing in a typical crystalline solid. So what would happen as a result in that, if you use the Inglis type of approach, you'd predict a fracture strength that's 100 times larger than the Griffith equation. So as in many things, when you talk about approximations, the Inglis approach and the Griffith approach are bounds on the problem. And in many things, when you talk about mechanics, as I say, materials never study mechanics or physics. So what happens is that the actual material behavior is somewhere between these extremes. The fracture stress does depend on the notch root radius, but not to the extent as indicated by that equation here. So the apparent discrepancy between the stress criteria and the energy criteria based on thermodynamics, you can resolve it by viewing fracture as a nucleation and growth process. So what that means is when you have your applied stress and you have a crack size that satisfies the Griffith criteria, so you go to the Griffith equation, so you have your crack size and your applied stress and your surface energy, and everything here looks like it would satisfy the criteria of the Griffith criteria. There's a sufficient thermodynamic driving force to grow the crack, but first there must be something to trigger, nucleate, or kick off the fracture process. And an example the book gave, which I kind of like, it's analogous to the solidification of liquids. When you cool water to 32 degrees Fahrenheit, 0 degrees Celsius, water turns into ice. But normally what triggers the water turning into ice is you have to nucleate or initiate this process. So it's either on the surface of another solid, such as your car windshield on a January morning, or you have a little piece of dust or something like that. So that's what the ice can form around. But when you suppress this nucleation, you can supercool, or at least momentarily, the water to as much as 30 degrees Celsius below the equilibrium freezing point. And the example is when you hear in the in the wintertime, you hear the forecast of freezing rain. That's the idea, is that when the temperature is below freezing, but nothing's triggered the water coming down from the clouds to turn into ice, so it comes down as rain, and it's only when the freezing rain, which comes down as rain, hits your windshield, it hits something solid, that's the trigger that turns it into ice. So it's the same idea. So it's the same idea as fractures, that even if you have all the other conditions, you need to have something to trigger the fracture. And usually things that trigger fracture have to do with local stress concentrations. So in the real world, surfaces have roughness. So at the tip of your flaw, there's a microscopic surface roughness at the tip of the flaw that can create sufficient local stress concentrations to start the failure process. So you just have that extra little thing, that extra little stress, very localized stress concentration, which is just enough to start the failure process. Or another thing which can trigger the failure, which I don't know, I don't remember if I did repeat the figure, forgot that. Or another situation is where you have a big you have a big crack, but you have a sharp micro crack near the tip of the flaw. So this flaw is a finite notch radius, but you have a very small sharp crack right at the tip of this crack. So what you have is that this macroscopic crack with the radius of curvature as shown in this equation here. So right in the area near the tip of this big crack, you concentrate the stress. You scale it, but you scale the rest the applied stress, because remember, you have this applied stress way out here. You have this applied global stress, but right in this area near the tip of this big crack, your local stress right around here is this local value, which is higher than the applied stress. So as far as this crack is concerned, when you applied the Griffith equation, going back here we go. So as far as the Griffith equation, the local stresses that are applied in the Griffith equation are not that applied stress, but the concentrated stress. And that'll cause this local crack to start propagating, because its local stress is high enough to trigger the fracture process. So then what happens is this little crack here, once it grows sufficiently, it'll link up with the big crack. And instead of just having one big crack and this macro crack, this crack will grow to the point it'll link up with this crack, and you'll just have this one big crack. And then with this bigger crack, with the bigger crack length, then if the Griffith equation is satisfied globally, because we'll have a bigger crack length, then this big crack will start to grow. So an advantage of this type of specific mechanism is in ferritic steels, it causes cleavage fracture. Let's see. Cleavage fracture. So any questions on this? Okay. So moving on. So So from the original Griffith equation, there were modifications that were made to this. So the Griffith equation, as developed and we talked about, is valid only for ideally brittle solids. So when you look at glass, which is the stereotypical brittle material, Griffith obtained a good agreement between his equation and the experimental fracture strength of glass, but the Griffith equation severely underestimates the fracture strength of metals because obviously metals are not brittle, they're ductile. And at a point, you even have local plasticity in there, which we'll talk about a little bit. But in another week or two, we'll get a lot more into what happens when you start getting plasticity at your crack tip. But anyway, Irwin and Orwan independently modified the Griffith expression to account for materials which are capable of plastic flows. So what we have, this is still our sharp crack, but instead of a brittle material, we have a material that's subject to plastic flow. So what Irwin and Irwan came up with was the idea that the fracture stress is equal to twice the modulus and twice the modulus, but instead of just the surface energy, we also have an additional energy, gamma P, which is the plastic work through per, and it's still to the 1/2 power, but we have this gamma P term, gamma sub P term here, which is the work generated by the plastic work per unit area of surface created. And this plastic work a lot of times is much larger than the straightforward surface energy. So that's, and for metals, things doing with plasticity is important because metals, because even as we'll talk about, even if macroscopically, and this whole idea with stress concentrations as we talked about, even though macroscopically you could be well below the yield stress due to the stress concentrations right at the tip of your crack, you could be, your local stresses could be above the yield stress and you'll have local plastic flow right at your crack tip. And this is something in another week or so we're even going to be going into a lot more deal on, is that it'll still be within the context of what's called quote unquote linear elastic fracture mechanics, but we're going to discuss what happens when we have local plasticity at the crack tip. So in an ideally brittle solid, a crack can be formed merely by breaking the atomic bond. So the gamma S is the total energy of broken bonds per unit surface area created. But when the crack propagates through the metal, you have dislocation motion, which is reflected as plasticity in the vicinity of the crack tip, which results in additional energy dissipation. Because don't cover in this class, but if you ever take a plasticity class, you know, when you get down to the atomic scale, what causes plasticity of metals is the motion of dislocations. So Irwin and Irwan originally derived that equation that we just wrote down for metals, but it's also possible to generalize the equation for any type of energy dissipation. So what we do is we just say that our fracture stress is equal to 2 times the modulus times this new term W sub F divided by pi and the half crack length all to the 1/2 power. So this W sub F term, that's going to be our new generic term to account for the fracture energy due to whatever. It's the energy due to the breaking of atomic bonds. It's the energy due to plasticity effects. It's the energy due to viscoplasticity effects, which we're not going to talk about much, if any here, but it's just the idea that it's just a generic energy to account. This is the energy resulting from a crack opening and creating new surfaces and the material plastically flowing. So this WSMF term will just be our generic term for energy. So the idea is depending on your material and the loading and various things, the fracture energy can be influenced by a whole variety of things which increase the surface area. So what we have is our ideally brittle material first, so this is our ideally brittle material where the only thing that leads to the propagation of crack is the breaking of atomic bonds. Then we have this case here, which also allows for plasticity, where we have the breaking of atomic bonds, but we also then have some plasticity right at the crack tip. So we have our failure. So our failure energy is both due to the breaking of bonds and the plasticity. And then we also have a more complicated thing which occurs in some materials, the idea of branching. So a lot of times in what we're doing, we're going to assume that a crack opens up and it just progresses in a nice regular way. But in reality, you can have cracks can form branches, cracks can go off in a variety of directions. So that's another thing which can affect the total failure energy, is that not just your crack one crack propagating in a nice straight way, but also you have your crack propagating in an irregular fashion. And there's certain materials and certain loading conditions where accounting for this is what you really want to do to totally account for the failure energy in your problem. So we'll finish this section with a quickie, fairly quickie example problem. So here's our problem again that we talked about. So we have a brittle material, and similar to what we talked about before, we have a big crack with a half length A1 and a radius of curvature rho. And here we have our mini crack, and then we have our mini crack right to the right of it with its own crack length located near the tip of the larger flaw. So what we need to find is what's the minimum size of this micro crack. So what's our value of A2 that's going to cause this mini crack to grow to the point where it'll then link up with the big crack and overall cause failure. And we'll be using just the Griffith criteria to solve for this. So what we have is that our nominal stress at failure for the big crack is, we have our failure stress is equal to 2 times modulus times our surface energy, and something I forgot to mention is that this mini crack here, this is a penny-shaped crack. So we're going to use the equation that I wrote for penny cracks. It's not a sharp crack. That'll be important in a sec. So anyway, so for our big crack, we have 2 times the modulus times the surface energy divided by pi divided by half of the crack radius for the big crack, all taken to the 1/2 power. And so that's the stress that will lead to failure. So that's the stress that will lead to failure of the big crack. And what we also know is that at the tip of the yeah, okay, we'll do this on the next slide. Yeah, so what we can say is the stress in the, so that stress we just wrote is the stress that would ultimately cause this big crack to fail. Now what we're going to do is we're going to look at what is the stress right here, right in the area of the tip of this big crack. And so for that, we can say that the stress at the tip of the big crack, and this is where we use the English criteria, so it's twice the global applied stress divided by the square root of the ratio of the half crack length and the radius of curvature. So what we can do then is we're going to, for the little crack, for the penny-shaped crack, for the failure stress, the stress that will result in failure of the little crack, the mini crack, because it's a penny-shaped crack, is equal to pi times the modulus times the surface energy divided by 2 times 1 minus the Poisson ratio squared multiplied by A2, all this to the 1/2 power, to the 1/2 power, and to the 1/2 power, and this A2 now is the half crack length of that mini crack, that little crack that's right at the tip of the big crack. So what we can do is, for this failure stress, we can take from before. We know for this failure stress, we know that the stress that this little crack sees is that concentrated stress, which is equal to 2 times the stress in the region of the crack multiplied by the square root of A1 over rho. But what we know from the big crack, we also know for this stress here, this stress here is the stress that will lead to failure. So by the Griffith criteria, that's equal to 2 times the modulus times the surface energy divided by pi times A1, all to the 1/2 power. So we take this stress and plug it in here. And so we get 2 times 2e gamma s over pi times A1, all this to the 1/2 power, multiplied by the square root of A1 over rho. And now this becomes and so we use this. We use this for the stress. So this is the stress that is seen by the mini crack due to the stress concentrations. So this is the crack. So this will be the stress that leads to failure of that mini crack, because this is the stress that it's subjected to. So this is what we set equal to pi times E times gamma S over 2 times 1 minus nu squared times A2, all to the 1/2 power. So now this is the only thing that's unknown here is A2. This is the stress that the little crack sees, and it's not just, and this is the stress that will cause that. This is the stress for the little crack, and it's all related to these other things related to the big crack, and we set it to the criteria which causes failure. So we say, so what we're solving for is what's the half length of the mini crack that will lead to the failure stress specified here. So from all of this, do we can do some algebra. So after some algebra, what we get is we get that A2 is equal to pi squared times the radius of curvature divided by 16 times 1 minus nu squared. Okay? So we use the big crack to say this is the stress in the area of the little crack caused by the fact that it's magnified because we have the big crack there. And then given that stress that'll cause failure, what's the crack size of the little crack that'll lead to that stress? Okay. So, couple of other points. For Poisson ratio of 0.3, which is kind of a Poisson ratio of 0.3, which is kind of a standard value of Poisson ratio. The size of this the size of the the half length of the mini crack is 0.68 rho, which would mean that the total crack length is, about 1.4 times the radius of curvature. Well, what this means is the nucleating microcrack, it's approximately the size of the crack tip mate radius. So I mean 1.4 is a little different, but it's not like it's 10, 100, 1,000. So so for this little micro crack to affect the big crack, it has to be at least as large as the crack tip radius. Now, this solution contains several simplifying assumptions, as most simple problems do. The notch tip stress computed from the equation is computed to act uniformly ahead of the notch in the region of the microcrack. In reality, what you'd have is that you would have your maximum stress here, and then as you start progressing along, you would have a decrease in your stress. So your stress, exaggerating a lot, would be something like this. We just assume that the stress right at the tip stays constant all the way along the length. So that's a simplified assumption. And the other thing that we didn't account for is the fact that because this is a boundary here, you would have some, you would likely have some boundary conditions involved. But this is a simplified problem. We're neglecting that, and it gives us an idea, and it's probably still, with everything in the dimensions and the effects of everything, it's probably still good enough. So, any questions on this? Okay, so this is actually a good point. So we'll take our break here and we'll come back at about 20 after. We'll get going again in just a sec. Okay, so now we're going to, and we'll be, starting this some today, moving, even more in the next week or two, into the types of parameters and methods that are practically used to solve engineering problems. So in 1956, Irwin proposed an energy approach for fracture. It's basically the same as the Griffith model, except that Irwin's approach is in a form that is, as I said, more convenient for solving engineering problems. So Irwin defined an energy release rate, and we'll call it G, which is equal to the negative of the derivative of the potential energy with respect to crack area. So this energy release rate is a measure of the energy available for an increment of crack extension. Now, an important point to note that when we talk about rate here, it's not that you normally think of rate in terms of the derivative of something with respect to time. What this energy release rate is the rate of change of potential energy with respect to crack area. And since this G is obtained from the derivative of energy potential, it's also called the crack extension force or the crack driving force. So and so based on work that we discussed earlier, and not go through the full derivation, but the energy release rate for a wide, so when we talked about the, so when we talked about before the energy, we talked about, let me find the, so we, oh, no, so we talked about before that here we go. So we talked about that the potential energy is equal to our initial minus pi times the stress square times the half length square times the thickness divided by the modulus. So based on that, so when we take our derivative with respect to the area, so we know that the energy release rate is the negative of the derivative of potential energy with respect to area. So from this equation, we get that it's equal to pi times the square of the stress multiplied by the crack length divided by the modulus, and this is all related to the idea that remember that the area is equal to the whole crack length multiplied by the thickness, and the total area of the crack is 2a, so it's 4 times AB. So when you put in those types of changes and you differentiate with respect to the area, you get this definition of the energy release rate. So based on this definition, we say that crack extension occurs when the energy release rate reaches a critical value. So this critical value is G sub C, which is also referred to as fracture toughness. So we can also say that, again, based on equations we had earlier, that it's equal to the derivative of the total surface energy due to the strain energy and the strain energy, plastic energy, what have you, with respect to the area, which is equal to twice of the surface energy. And the potential energy of the elastic body is equal to the strain energy stored in the body minus the work done by external forces. So what we can do with that is we'll look at a couple of simplified cases. We're going to look at a cracked plate that is dead loaded, and by dead loaded you can see it's constrained here, and we hang a weight to the bottom of this plate, so we can assume that we just have this one distributed load applied here, and by the fact it's here, that the effects of this weight are evenly distributed across the whole bottom edge of our plate. And since the load, we assume that our load is fixed. This P is a defined load. So because of that, we say that this structure is said to be load controlled because we're controlling the load that is applied to the structure. So what we can do is first, we'll do it here. So first we can say that the external work is just equal to the load multiplied by the displacement due to that load. So before we do anything, before we extend the crack, it's basically the area underneath this big rectangle here. So that's the external work, and the strain energy is equal to the integral from displacement 0 to the displacement of the load times the increment in displacement. And so if we look here, we apply, and with our initial crack length, we have initial here. So this is our initial load, this is our initial displacement. So by the integral, it's just the area underneath this triangle here. And so we can just say that the strain energy is equal to 1/2 the load times the displacement. So it's just the area underneath this little triangle here. So we can specify the potential energy and fracture toughness as follows. So we know that our potential energy is equal to the negative of the strain energy, and we negative of our strain energy, and we know that our strain energy release rate is equal to the negative of the derivative of the potential energy with respect to area. And when we talk here, we're also talking about this B term here is the thickness of the plate. So what we have is it's equal to 1 divided by the thickness of the plate times the derivative of the strain energy with respect to the crack length. And this is all for the case of a constant load. So we have it's equal to 1/b times dA of 1/2 P delta. So, and what we can do is we can pull 2's a scalar, we can pull that out. It's a constant load, so we can pull that out. So it's equal to P over 2 times B times the derivative of the displacement with respect to the half crack length, all for the case of constant applied load. Okay. Now there's another case there's another case we can look at. Now it's the same type of thing. We still have our play with the crack, but now instead of an applied load, now we apply a displacement. So what we have here, so when the plate is displacement controlled, we know that our force is equal to 0, and we know that our potential energy is equal, the energy due to applied forces is equal to 0, and yeah, the work done by external forces is equal to 0 because we have no external forces, and we know that the potential energy is just equal to potential energy. The potential energy is just due to the strain energy. So by the same type of idea, we can say that our so by the same type of idea, we can say that, yeah, by the same type of idea, we can say that the strain energy release rate is negative 1 over B, the derivative of the strain energy with respect to the crack length, only holding the delta constant, and yeah. Yeah, so when we do that, and so the difference here is now similar to what we have here, except instead of pulling the load out, we can pull the displacement out because the displacement is constant. So when we do that, what we end up with is that our strain energy release rate is negative delta over 2B times the derivative of the load with respect to crack area, all for the case of a specified displacement. So these are extreme cases, and in a little bit we'll talk about what happens when you don't have the extreme cases. But what we have is But for right now, what we'll do is we'll introduce a term called the compliance, which is the inverse of the plate stiffness, and we're going to say that this compliance term is equal to the displacement divided by the load. And so given that, we can manipulate the equations we had. So for example, for the case of the applied load, we had the strain energy release rate is equal to the load over 2B times the derivative of delta with respect to A, all for the case of applied load. So we can substitute in from this expression here, we know that delta is equal to the compliance times the applied load. So we have P over 2B times the derivative with respect to A of the compliance times the load, and yeah. Compliance by the load, and we can, yeah. So we can pull once again the load out. So we have that the strain energy release rate is equal to P squared over 2B times the derivative of the compliance with respect to the crack length. And if you go through a similar argument, you get the same equation for the case of displacement control. So it's just plugging in the definition and still using what's constant. And obviously what you do for the second case, you would say that the displacement is equal to the compliance over the load. You pull things out, or do the derivatives, and you get that same idea. So this equation is demonstrated graphically in this figure. So what we have is here for the case of load control, a crack extension. So if we go from A to A plus dA, it results in a net increase in strain energy. We have this additional energy here resulting from the increase in load. I'm sorry, the increase in we have the increase in load. So what we have is that so for low, okay, it's demonstrated because, what it is that the increase in displacement, leads to the increase in crack length, and that's what leads to this extra area here under the curve, which leads to our increase in strain energy, and thus our energy release rate. And so so here we go. So what we have is that, and by the way, by something I forgot to write down before, the energy, we can also say that the derivative of the strain energy with respect to crack length for the case of load control is equal to the negative of the derivative of the strain energy with respect to crack length for the case of displacement control. But anyway, what we have is, for the case of load control, we can have our increase in strain energy for the case of load control is equal to, if you manipulate the geometry of the figures, we have P times D, the change in displacement, minus 1/2 the 1/2 times the load times the change of this. 1/2 times the load of change of displacement. So it's just equal to 1/2 of the load times the change in displacement. And this is due to the idea where we take the new energy due to this revised triangle, and we subtract off the energy due to the previous one. And so that's how we get that. And conversely, when the displacement is fixed, the change in the work due to external forces is 0, and we can also get that the change in our strain energy due to displacement is equal to differential of the load times the displacement divided by 2. And this change in load term is negative. So the absolute values of these energies differ by an amount, dP times d delta divided by 2, which is negligible. So what we can say then is, for are cases of load control and displacement control that are change in strain energy due to load control is just negative of the change in strain energy due to displacement control. Okay. So now for a practical application of this, what we're going to do now is we're going to determine the energy release rate for this double cantilever beam specimen here, where we have a thickness equal to B and we have a opening of the displacement delta of that the between the top and bottom surfaces, and we have our crack length equal to A. So the way we'll do it is these equations just come from beam theory. So we can say that this displacement, half of the displacement is equal to the load times the crack length cubed divided by 3 times the modulus times the moment of inertia, and the moment of inertia is equal to the thickness times the height cubed divided by 12. And when we talk the moment of inertia, we're talking the moment of inertia of this half section here. You see that the h is the height of this half section here. So what we can say is we know that the compliance is equal to the displacement over the load, and taking this equation here and just manipulating it a bit, we get it equal to 2 times a cubed divided by 3 times the modulus times the moment of inertia. So now what we can do is we can then we know that our energy release rate is equal to p squared divided by 2b times the derivative of compliance with respect to the crack length A. And so we now have our compliance is very nicely defined in terms of the crack length. So we can just take this so we can just have our p squared over 2b times the derivative of this with respect to A. So it's equal to 6. So it's equal to 6a squared. So it's equal to 6a squared. Yeah. Over 6a squared over 3 EI. Our 6, 2, 3 cancel out. So our 6, 2, and 3 cancel out. So we get our energy release rate is equal to p squared, a squared over b times e times I. And now we substitute the I is equal to 112 b h cubed. We substitute that in for I, and we do a little bit of algebra. We get 12 times p squared times a squared divided by b squared h cubed e. Okay? Okay. So the next topic we're going to go into is instability and something called the R curve. So we knew when we talked about the crack extension occurs when the strain energy release rate is 2 times the surface energy. but the crack growth can be stable or unstable depending on how the strain energy release rate and the surface energy vary with the crack size. So a stable crack growth will mean you apply a little bit of load, you get a little bit of growth in your crack, you apply a little bit of load, you get a little bit of growth in your crack, and it just keeps on that way. Unstable means that the second you apply any increase in your load, your crack will just take off like mad, and there's no stopping it. So the term that was developed to represent the stable and unstable behavior, this 2WF term was replaced with a term signified by the letter R, which is the material resistance to crack extension. And you can plot this resistance versus the crack extension versus the crack length, and it's called a resistance curve or an R curve. And then you can also plot the strain energy release rate versus the crack size, and that's called a driving force curve. So we'll start off is we'll consider our wide plate with a through crack of initial length 2a sub 0 and at a fixed remote stress sigma, the energy release rate varies linearly with crack size. So we developed this before. Our energy release rate is equal to pi times the square of the stress times our half crack length divided by the modulus. And this figure shows the R curves for two types of material behavior. So in this curve here, the R curve is flat, which means that the resistance is for your initial crack size, that when you increase your stress, the resistance doesn't change and it stays constant all the way until you hit this stress sigma 2. Once you hit the stress sigma 2, then your crack goes unstable and it just grows like mad. So fracture occurs when the stress reaches the stress sigma 2, because that's where you have unstable crack growth, because the driving force, the strain energy release rate, this keeps increasing with crack size, but the resistance remains constant. So when the driving force keeps growing, but the resistance remains constant, you just have an unstable crack and the crack grows like crazy. Now, the second case represents a material with a rising R curve. So what happens here is your resistance stays constant for a while, and when you hit the sigma 2, the resistance grows a little bit, but it doesn't go crazy. So the crack can't grow any farther unless your crack increases. The stress increases. And when the stress is fixed at sigma 2, the resistance, this black curve here, grows faster than the driving force. So what it means is that the driving force is growing, but the resistance is growing at a faster rate. So obviously, if the resistance is growing at a rate faster than the driving force, you're not going to have unstable crack growth. Things will still be under control. However, when you hit this and the same is true even when you go to sigma 3. When you go to sigma 3, because when you hit the stress sigma 3, because the rate of increase of your driving force is still less than your resistance. However, when you get to sigma 4, all of a sudden your resistance curve is tangential to your driving force curve. So what happens here is is it becomes unstable, because once you get to this point, all of a sudden now your driving force, the slope of this sigma 4 line, is greater than the slope of this resistance curve. So this is the point where finally, once you reach sigma 4, the rate of increase in your driving force is greater than the rate of increase of your resistance, and then that's what leads to your growth and the unstable growth of your crack. Okay. And in words, that's all this is, which I just said. So the conditions for stable crack growth can be said is that when your strain energy release rate is equal to your in your resistance, it's stable. And when the rate of increase of your strain energy release rate, your driving force, is less than or equal to the increase in your resistance at the rate of increase of your resistance as a function of crack length. And as we talked about, unstable crack growth then occurs that when the rate of increase of your driving force, the strain energy release rate, becomes greater than the rate of increase of your resistance. Now, one thing to note is that when your curve is flat, you can unambiguously define your fracture toughness, your critical value of energy release rate. It's very simple. When you hit this particular value of energy release rate, it goes unstable and your crack grows like crazy. So this one is easy. However, for your material with the rising R curve, it's a lot harder to determine uniquely a single toughness value. So by this equation, we say that the unstable crack growth occurs when the rate of change of your strain energy release rate is greater than the rate of change of your resistance. However, this point of tangency, the point where it becomes tangent, depends on the shape of your driving force curve. So it depends on the shape of your strain energy release rate with respect to crack size, and that depends on the configuration of your structure. So for this flat curve case, no matter what your crack looks like, when you hit this critical strain energy release rate, things fail. However, what happens is this slope of G, the curve of strain energy release rate versus crack size, that's different depending on whether it's a through crack or a DCB specimen or different types of configurations. So for the through crack in a flat plate, it's linear, but in the double cantilever beam example, as we talked about in our example problem, for our example problem, G increases with the square of the crack size, where in our baseline equation for a through crack, G increases linearly with the crack size. So this curve here will look, for the case of a through crack, these are nice linear curves. For a DCB specimen, they would be quadratic curves. So then it's still the point where the resistance would still have the same shape, but the slope of the shape of this strain energy release rate versus crack size, that'll be different. So the different configurations have different GC values for a given R curve. So materials with rising resistance curves can be characterized by the value of the strain energy release rate with the initiation of crack growth. And this initiation toughness is usually not sensitive to structural geometry, but there are other problems with this measurement. And one of the big ones is that for most materials, if you're doing a fracture test, it's hard to determine the precise moment of crack initiation. So and we'll talk about this later in the semester when we talk about test techniques, but an engineering definition of initiation, similar to the idea that when you do yield analysis of metals, you probably learn that you use a 0.2% offset, that you say that the yield stress occurs when you have 0.2% plastic strain. And so that's one way to look at it. And another limitation of this initiation toughness is that it characterizes only the onset of the crack growth, and it provides no information on the shape of the R curve. So it's just one of these things to say that the typical type of thing that you see in engineering, where we talk about the theory, things look great when we put on paper, but when it actually comes time to do real experiments and excuse me, really characterize things, things aren't always quite that easy. You don't get distinct curves as what happens. And the point here is that where it relates to here is with this idea that the value at the initiation of crack growth, it's what it's all is determining this A sub 0, is we can say in our theory, oh, our initial crack size is obviously this. But what this whole discussion related to the idea is that when you do a real experiment, determining that precise point where you get a crack in the structure, that's not so easy. So what we generally say is within some delta, some limit, we say, okay, when we see the crack and it's within some limit, that's what we call our initial crack size. And we just note that this A sub 0, there's a strong likelihood, may not be totally accurate. Okay. So the R curve. So the reasons for this R curve shape. So some materials exhibit a rising R curve, as we talked about. For other materials, the R curve is flat. And the shape of the R curve depends on the material and to a lesser extent on the configuration of the crack structure. So for an ideally brittle material, we have our flat R curve because it's an invariant material property. However, where we get these rising R curves, so for glass, we have something like this. However, for metals, where we have some localized or not so localized plasticity taking place, for a nonlinear material behavior, the R curve can take on a variety of shapes. For example, ductile failure in metals results in that rising R curve that we showed because the plastic zone at the tip of the crack increases in size as the crack grows, which means that we'll have a growth in resistance relating to the plastic flow, because when the material is deforming plastically, that energy that may go into the propagation of cracks instead goes into the propagation of the plastic flow in the material. So the driving force has to increase in these materials to maintain crack growth. So if the cracked body is infinite, so what that means is if we have a plastic zone that's really, really small compared to the dimensions of the body, the plastic zone size and the resistance eventually reach some steady state value, and then instead of just a continually increasing R curve, it's kind of hinted at here, at some point the R curve reaches some asymptotic value and even goes somewhat flat. And what's even crazier is some materials can display a falling R curve. So for when a material fails by cleavage, for example, the material resistance provided by the surface energy and the local plastic dissipation. So if crack growth were just stable, the R curve would be relatively flat. However, cleavage propagation is normally unstable. The material near the tip of the growing crack is subject to very high strain rates, which suppress plastic deformation. And the resistance of this rapidly growing cleavage crack is less than the and initial the initial resistance at the onset of fracture. So this is the idea of static friction versus sliding friction, where it takes more force to move a stationary object from its initial position than is required to maintain the sliding motion. That's the same idea, is that if you're starting to have an increase in things, things start to move, things start to deform. It takes less energy to keep things moving. And as we talked about a little bit, the size and geometry of the crack structure can exert some influence on the shape of the R curve. So a crack in a thin sheet produces a steeper R curve than a crack in a thick plate because for the thin plate, it's more close to a plane stress problem. So we have a low degree of stress triaxiality at the crack tip, where in a thick plate, not only is it not plane stress, but it may actually be in plane strain. So you'll have stresses in all your directions. And if you have stresses in all your directions, it increases your local stress concentrations, which can facilitate crack growth. And just if this wasn't all complicated enough, the R curve can also be affected as you approach a free boundary. So a wide plate may exhibit a somewhat different crack growth resistance than a narrow plate, because when your crack gets near your boundary, all of a sudden you have boundary effects that come into play, and boundaries promote stress concentrations, which is another thing which can lead to the growth of your cracks. Now, in a perfect world, the R curve, as well as other measures of fracture toughness, should be a property only of the material and shouldn't depend on the size or shape of the cracked body. Because when you're designing a structure and using a material, you want something that you can look up in a handbook and say, this is the value. I plug this into my hand calculations, my analytical methods, or my computer code, and say, this is what I can do. This is what I use. And usually in fracture mechanics, a lot of these properties we talked about are listed as material properties. But just something to keep in mind that effects due to configuration can occur. So when you do your analysis and you see something that doesn't look quite right, you can start. The idea is to think about, and we can't here cover all the possibilities, but just to keep in mind that if you see something that doesn't look quite right or your analysis doesn't give quite the right results, one of the things when you're looking at in terms of what could be causing your errors, to look at your configurations and to think various things. How can your configuration of your structure be contributing to local stress concentrations, which could lead to errors in your analysis? Okay. So a little more on our discussion of the R curve. So it's load control versus displacement control. So the stability of the crack growth, as we talked about, depends on the rate of change of the strain energy release rate, or which is the second derivative of the potential energy. And this driving force is the same for both load control and displacement control. The rate of change of this driving force depends on how the structure is loaded. And displacement control tends to be more stable than load control. So like as shown in this figure here, with some configurations, when we talk about displacement control, that's these dotted lines here. When we increase our crack size, we actually have a decrease in the strain energy release rate as a function of crack size. So let's look here as an example. We have a crack structure subjected to a load P3 and a displacement delta 3. So if the structure is load controlled, so it's this load curve which determines how things vary. At this point here, the tangent of our resistance curve, or our curve, which is this thick line, the tangent of this resistance curve is equal to the tangent of our strain energy release rate. Our strain energy release rate is with respect to crack size for this load. So as the crack goes beyond here, the slope of this P3 curve is greater than our R curve, so we'll have unstable crack growth. However, if this was displacement controlled, where we control the displacement, the structure is stable because even as the crack size grows, our slope of our resistance curve is greater than the slope of our strain energy release rate curve. So we have stable crack growth, and for unstable crack growth for further crack growth to occur, we actually have to increase our displacement. So that's what'll allow our driving force to be at the point where things will actually grow. So the R curve is determined experimentally, but the trick is usually when we do experimental tests, we do displacement control most of the time because displacement control is a much easier test to do than load control. You can control displacement, but when you do a lot of times it's hard to do a load control test. So since most of the common test specimen geometries exhibit falling driving force curves in displacement control, you can get an awful lot of stable crack growth. And if an instability occurs during the test, the R curve can't be defined beyond the point of ultimate failure. Okay. So one more example problem. So we're going to evaluate our relative stability of our DCB specimen in load control and displacement control. So from the result derived earlier, we found out that our strain energy release rate is equal to P squared times A squared over B times E times I. And when we substituted in the definition of the moment of inertia, we got 12 times P squared times A squared divided by B squared H cubed times E. And for the case of load control, we can say that the derivative of our strain energy release rate with respect to crack size, and we did this problem for the case for the case of load control, we can say that the derivative of the strain energy release rate with respect to crack size, holding P constant, what we get is that it's equal, when we do the math, we get 2 times P squared times A divided by B E I, B E I, and yeah, yeah. So we go back, we're just use this expression when we did the derivative. And if we look and we compare to our initial definition of the strain energy release rate, we can say that it's twice the strain energy release rate divided by the crack length. Now, for okay. And for displacement control, so for the case of displacement control, we express the strain energy release rate in terms of the displacement and the crack length. And from beam theory, we can find that the load is equal to 3 times the displacement times the modulus times the moment of inertia divided by 2 times the crack length cubed. So taking this expression into the expression for energy release rate, what we get is our energy release rate is equal to 9 times the displacement squared times the modulus times the moment of inertia. Oh, and this negative here divided by b times a to the 5th. And that's, if we simplify, it's -4 times the strain energy release rate divided by the crack length. And what we did here is we know for displacement control what the P is, and what we did is we just took that P, we stuck it in here, we squared the P, and we canceled terms, and we did some algebra. So what we can say is, so the point from this is that the point from this is that the driving force, the rate of change of the strain energy release rate with crack length, it increases with load control because this is positive, and because this is negative, it decreases with displacement control. So for a flat R curve, so for that example we talked about before, the crack growth in load control is always unstable, while displacement control is always stable. Okay. Now, the last thing we'll cover today is, okay, in real life, most real structures aren't pure load control and aren't pure displacement control. So a simple way of representing this is we have a spring in series with this structure. So we have a structure with the crack, and we have a spring and it's in series with this flawed structure. So the structure is fixed at a constant remote displacement, and the spring represents the system compliance. So for the case of pure displacement control, the Cm would be equal to 0 because the spring would just provide no resistance. The only resistance we have is we just have the applied displacement. And however, for load control, if we set the Cm equal to infinity, what we have then is we just pull on it, the spring provides no resistance, and all we're doing is we're just providing a load to the structure. So when the system compliance is finite, the point of fracture, so when the system compliance is finite, somewhere between 0 and infinity, the point of fracture obviously lies somewhere between the extremes of pure load control and pure displacement control. However, determining the precise point of instability requires a rather complex analysis. But, if you have the book, in the appendix of chapter 2 of the book, they go through this derivation in the detail. But for now, what we'll do is we'll just give the results. So for instability occurs at the point where the strain energy release rate is equal to the resistance, and we know that the rate of change of the strain energy release rate with respect to the crack zone size is equal to the rate of change of the resistance with respect to the crack zone. And you can derive, we won't go through it here, it's a complicated analysis, that this rate of change is equal to the partial derivative of the strain energy release rate with respect to crack size, with respect to, for the load, minus the partial derivative with respect to load of the G with respect to load for crack size times the derivative of partial derivative of the displacement with respect to crack size for the case of the load, and all this multiplied by the compliance plus the partial derivative of the displacement with respect to the load for crack size, and this is all inverted. So it's a complicated equation, but it's just the idea that everything else we did today were for simple cases of pure load control and pure displacement control, but in reality, the world isn't pure load control or pure displacement control, so it's obviously a much more complicated analysis, but there are methods to determine the onset of instability for these more complicated situations. So, any questions? If not, that's it for today. Have a good week, and I'll see you guys soon.